speaking about event attribution. I was trained as a statistician, so I'm trained in one of the black arts, and I've spent my career in climate science. But you have to understand that it's one of these black artists that is going to be talking to you. What I do in my spare time, such as it is to take the odd photograph, and so you'll be seeing quite a few photos as we go along where I'm the person behind the lens. There are a few others that I've acquired from other places as well. I'm going to be talking about event attribution. It's a new aspect of climate science, and it's often what we're asked to do in the wake of an event such as the Horse River Fire or the Calgary floods, where we're asked to say as scientists whether or not we think human influence on the climate system played a role in that event. So I'll be talking about that lots more. I have an introduction. I'll give you an overview of extreme event attribution, of the science as it stands at the moment, the kinds of questions that are posed, and then I'll discuss at least the Horse River Fire, and if I have some additional time, the Calgary floods and perhaps more. Many acknowledgements at the bottom, both sources of funding for this work and people who have contributed to this work. So I'll be reporting some work in progress that's being undertaken by a young postdoc in Victoria, who's an extremely talented young lady, Megan Kirschmeyer-Young. The context for this talk, this is a thing that, and this setup's a bit awkward. I'm used to looking at the screen. This is a kind of, so the context is, one of the contexts is the extreme amount of reporting on extreme events that takes place in the media. So a recent Google News search asking questions about articles reporting on extremes noted that there were 55,500 items that referred to extreme weather. This was over the course of a year, ending February 2016. 17,500 items that referred to drought, 34,000 items that referred to floods. This is in the Canadian media, so there's just enormous interest in this. If you did a similar search for 2006, you find almost nothing, and I don't know if that tells you something about the state of the Google database, or the level of reporting that's taking place, or the desperation that the media feels to fill their pages and blogs with information. There's certainly a huge amount of information and reporting at the moment. The public perception is that the frequency and intensity of extremes is increasing. We're certainly aware of a growing economic impact, and we're all aware of that. If you own a house, your property insurance premiums have been rising at a very rapid rate in order to cover costs of events that happen elsewhere. And so we've been experiencing probably double-digit inflation rates on property insurance over the past 5, 6, 7 years. But we're aware of the impact in many other ways as well. And it's a growing insurance industry concern. A notable voice is the Munich Re, a large reinsurance company that publishes a report annually, maintains a large loss event database, and reports on the contents of that database on an annual basis. When you read the media, the discourse very quickly tends to evoke possible links with climate change. And it does so in a relatively unconstrained way. You can find this after every large event and almost during the course of the event. And as a default, what we end up doing as scientists is kind of aiding and abetting the process. So somebody rushes up with a microphone and says to you as a scientist, well, it was this latest thing, the Horse River Fire, due to human influence on the climate system. And it's just happening. It's happening right at the moment. Then you have to respond honestly, and so you say no. I don't know. We have to study this. And so the reporter kind of gives you a hang-about face, and he's very disappointed because there isn't a sound bite, nothing to write about. And so you go a little bit further because you don't want to disappoint. And so the next thing you say is, but it's like, the thing that's just happened is like the kind of thing that we expect to happen as a consequence of climate change. And so, of course, that's generally an honest response, but it's also a dishonest response. We're aiding and abetting the process because we're inviting the reporter to make an attribution that we're not willing to make scientifically ourselves. And so that poses a serious communications challenge. So this thing called event attribution science has emerged over the past decade, and it's trying to fill that void. It requires us to do very rapid response science. These days, event attribution, formal event attribution, using available climate models and data can sometimes be done in a week for some examples of events that occur. The very first events, studies, took a relatively long period of time. So the first study that was published was a study published in 2004 describing the role that humans played or might have played in the 2003 European heat wave, which killed 35,000 people, according to some reports. But initially, the response time for the science was actually, on average, substantially longer than that. There was a paper published a decade after a flood in the UK, indicating that there was some human influence on the occurrence of that flood. And it took that postdoc a very long time to get tools and models and data together and to synthesize results and to provide assessment. We need to do much faster than that, much better than that. Very recently, there was a report published by the US National Academies of Science on event attribution. So that indicates something about the evolving maturity of this now at the stage where it's possible to write a couple of hundred pages and to produce some recommendations. So I was a member of that committee. Okay, so the public asked, did human influence on the climate system cause the event? That's the usual question. And that's a question that's really difficult to answer. And so what most studies attempt to answer is, did it affect the odds of that event? So that's kind of a risk-based question. Did it alter its magnitude? That turns out also to be a risk-based question because we're interested in the distribution of magnitudes under some set of conditions, and then we want to know whether or not that distribution was different at the time of the event than it might have been previously in an earlier climate. Some people, there's quite a bit of discussion in this little community that thinks about this, and some people think that we really should reframe the question. So rather than did human influence, begin a sentence by saying did human influence, okay, that requires comparison with a counterfactual world, a world where there is no human influence on the climate system. Rather than that question, these people argue that we should ask, well, how much of a given storm's precipitation, extent of a fire, and so on, is due to the attributed warming on the climate system. So we live in a climate system with an elevated concentration of greenhouse gases, where the body of evidence that is available to indicate that humans have had some influence on that climate is actually very strong and compelling, at least with regard to temperature. It's much less that we can say about precipitation, storm systems, circulation. But with regard to temperature, there's a very strong body of evidence, and there's very little to counter the notion that the run-up in temperature that we've observed during the past century or so is not due to us. Most studies, though, still compare factual with counterfactual climates, and by counterfactual, we mean the world that might have been had humans not emitted the 600 or so gigatons of carbon that have been emitted since pre-industrial. Just to put that number into context, by the way, the science now tells us that in order to stay under 2 degrees warming relative to pre-industrial, which is a number that's very extensively discussed in policy circles and at international negotiation, to stay below 2 degrees with a fighting chance, probability greater than 66%, we need to keep total emissions to less than 1,000 gigatons. Okay, so we're 60% of the way there, if that's what our target is. But that's simply as a side comment. These studies almost always deal with a class of events rather than an individual event. So an event happens, and that event is then used to define a class of events, the things that are as extreme or more extreme in some sense than the thing that has just occurred. That's usually what the discussion is about, and almost all studies use a probabilistic approach. I'll be giving you more detail about that in a moment. There's a very nice paper by Ted Shepard, a Canadian who now works at the University of Reading in the UK, and he defines this as a risk-based approach, and he contrasts it with a storyline type of approach. What the person who was arguing against the factual versus counterfactual approach was discussing was essentially a storyline-based approach, which says this particular event happened under these particular circumstances. There was this much more moisture in the air that contributed to that extreme precipitation amount. He was talking about a flood in Boulder. That moisture came from this particular source. That source was that much richer in moisture because sea surface temperatures had been warmed by 3/4 of a degree due to human influence on the climate system. None of that is quantified from a probabilistic perspective, but it describes a mechanism that leads to the particular event that occurred, and that's what in this literature is being referred to as a storyline-based type of approach. Okay, well, so if you look at this National Academy of Sciences report, you'll see this word framing used over and over again. And this refers to a whole bunch of things that need to be taken into consideration when designing a study. The event type that you're considering. Are you considering a class of events, all of the things that are more extreme than a particular thing that has been observed, or a storyline type, or an individual event? The analysis approach, is it risk-based or storyline-based? Event definition, what is the spatial scale, duration, and so on. I'll be talking about that a little bit more. And to be frank, this National Academy of Sciences report struggled with these things quite a lot. As you read through the report, you'll see it's stumbling on words. So we still don't have the words down quite right in order to allow us to be able to distinguish these things clearly. So which risk-based question, if we're going to take a risk-based approach, which risk-based question do we ask? Do we ask about odds? Do we ask about magnitude? And what factors do we need to take into account when considering the event? It's what statisticians call conditioning. What do I condition on? Sea surface temperatures are often conditioned on, so it's a pattern of the particular distribution of sea surface temperature anomalies that we see at a particular time. Whether or not an El Nino is taking place, whether the Pacific Decadal Oscillation is in a positive or negative phase, these things are thought to affect circulation and therefore affect moisture transport onto the land surface. And so they might be factors that affect the likelihood or magnitude of an event. So do we take those kinds of things into account? So those are all different kinds of questions that need to be thought about in the framing process. In other words, how the question is asked affects the answer. So how is the event defined? And so here's an example of the 2003 heat wave example. What you see in that panel in the upper left is a figure that shows, compares a 30-day period beginning the 20th of July 2003, temperatures during that 1 month compared to the average of the same month 4 other years, 1 year after, 3 years before. So within this very current 5-year period. And you see that the large part of Europe was substantially warmer than normal by a large amount. But it's a little bit difficult to draw a contour that says, this is the area that was most strongly affected by the heat wave. In fact, the largest impacts were in Paris, here, not here, in the south of France, where the temperatures were the highest. And so it's a little bit difficult to define exactly what the event is. The local definition of a heat wave will be very different from one place to the next. And so what these people did, Peter Stott and colleagues at the UK Met Office did, was to consider not the event specifically itself, but average summer temperatures in Europe during the summer of this heat wave. And that provided the background conditions against which the heat wave actually occurred. And so the question that they posed was about that heat wave. This little X here shows the observed temperature anomaly for that summer for this regions covering most of southern and central Europe. The observed trace goes like this. There's 2003. So it's extremely hot. It was about 5 standard deviations above some measure of normal. The climate model that they used shows this kind of variability between different simulations. And it follows the historical evolution from 1900 to 2003 really well. And then you see projections for the future. And you see that this 2003 event will become common in the future. But at this point, it's still extremely rare in this climate model simulated world. And their estimate was, in fact, that that human influence on the climate system had made that event about 4 times more likely than it would have been in a stationary climate, or a climate affected only by natural influences on the climate system. So that's one framing question, one aspect of framing. How do you define the event? Another aspect of framing is, well, which risk-based question do you ask? Do you ask about the frequency of an event, considering all temperatures above some particular level, or do you ask about the magnitude of the temperature that was observed? Both involve the creation of some kind of probability distribution and then asking questions about that probability distribution. And so the example here is the July 2010 heat wave over Russia. This was a very high impact event. It was in the news throughout the world. Air quality was extremely low due to wildland fire. This is the area that was affected. These are 2 probability distributions that were constructed, one taking current composition of the atmosphere into account, and one taking a pre-industrial composition of the atmosphere into account. And then if the question is about the magnitude of the event, you see that this is the event here, that the magnitude of the event wasn't that much larger under the forced climate conditions of the late early 21st century, but that the frequency was substantially higher. And so if you're looking at frequency, then you would argue, well, humans had a substantial influence on the occurrence of this event. If you're looking at magnitude, another paper argued, well, there's hardly any discernible influence of this human influence here. And so the answer that you get depends a little bit upon how you pose the question. And so there was a third paper that pointed out that really we should be answering both questions at the same time. Okay, so a little bit of statistics. You can run away now if you like. What I've written down here is a probability distribution, and I've considered temperature here. So the question here is about, well, it's still a framing question, so what factors are controlled in the analysis? I think I need to speed up a little bit, Jen. And the point is that there are studies that compare factual with counterfactual world and don't condition on anything else, or there are studies that compare factual with counterfactual world under certain sets of conditions, such as the prevailing pattern of sea surface temperature mountains. And so that needs to be understood when these studies are being taken. This approach, conditioning on something, has become very attractive because it enables us to use tools that are computationally much cheaper. But we can use atmospheric climate models rather than global climate, coupled climate models, and we can run the atmospheric climate models much more efficiently. We can do many, many more runs. We can in fact use PCs that people volunteer. We heard about volunteerism this morning. So this is something that people volunteer for. It's a little bit like SETI at home, to search for extraterrestrial intelligence at home. You can run a climate model at home. Go to climateprediction.net and find out about it. The experiment runs on your model, on your computer for something like a couple of months in the background, and at the end of that couple of months, a couple of gigabytes of data ends up being transferred back to the people who are organizing the experiment. The experiments can be set up so that you can access tens of thousands of runs. But the models need to be cheap, and so these tend to be atmospheric only runs. Okay, a couple of numbers that come out of these kinds of analyses. There are 2 key numbers, and one is, this is also used in medical science. It's a fraction of attributable risk, also called the probability of necessary causation. And what this is the increase in probability of the event defined in some particular way, the present climate versus a previous climate divided by the current probability. So if this increases, a typical fraction of attributable risk might be 25%. So 25% of the odds of the event today are due to human influence on the climate system. We've raised the likelihood of the event by 25%. Okay, so this is a key number, and it tells us something about whether or not the thing that we're asking about, human influence on the climate system, is necessary for the event to occur. So probability of necessary causation. There's another number called the probability of sufficient causation that can be calculated, and that tells you something about whether or not the factor that you're investigating, increased concentrations of greenhouse gases, are sufficient to have caused the event. That's a different number, and if that number is large, that means the event should be happening all the time now, as opposed to in a previous climate, because elevated greenhouse gases would be sufficient. Okay, let me move on to the Horse River fire. Here are some images that I gathered from the media. Two kinds of exoduses of people and of wildlife, impacts on people. People who were housed in Edmonton, people who lost their properties. 590,000 hectares burned, 88,000 people displaced. 2 fatalities only, indirectly through a traffic accident, not within Fort Mac itself. 2,400 homes lost, 665 work camp units destroyed, 3.6 billion in insured losses. I'm not sure what the number is for total losses. This may end up being the most expensive loss event in Canadian history. Calgary was $5.7 billion, only $1.65 billion was insured, the rest was uninsured. The difference between flood and fire insurance, as Paul was pointing out to me this morning. Okay, we're studying this, so this is a quick report on some work in progress. We're trying to ask an event attribution question, and we're trying to pose a question that is tractable with the tools that we have available, so climate models that we have available. So what we're doing is considering wildfire index values averaged across this region, region 9 here. It's the South Prairie homogeneous fire regime zone is defined by NRPen, I believe. This rather odd-shaped region. It, over some period of time, has had losses of the order of 10 or 12 times 10 to the 4 hectare burned per year. So it's some 1,000 or 1,500 square kilometers per year burnt in that zone. We're studying a bunch of fire indices. So these are the Canadian fire indices, fire weather index, the fine fuel moisture code, duct moisture code, drought code. And these are all indices that depend on temperature, relative humidity, wind speed, and precipitation. And so we need sources of data in order that we can study these indices and how their distributions have changed or how they might have been different in some sense over the course of the Horse Creek fire. We use the Canadian Earth System model. It's a relatively well-performing model that's assessed by the IPCC. It would rank somewhere in the top third of global climate models. We're using it in particular because they have recently produced a very large ensemble of climate change simulations, and so that enables us to estimate probability distributions. But it's a model at a relatively modest scale. So what we're showing here is the spatial, the surface topography as represented in that climate model. This is the observed surface topography according to some digital elevation model. This is the surface topography in a high-resolution reanalysis. We somehow or other need to get from this scale to this scale, do some bias correction before we can actually calculate these indices. And so we do that using a sophisticated statistical downscaling approach. Having done all of that downscaling and calculated these indices from these 50 simulations, then we have 50 simulations both under current climate forcing conditions, taking greenhouse gases, aerosols, land use change, and the lot into account, and taking just natural forcing conditions, so the effects of volcanic forcing, the effects of changes in solar output into account. So we can come up with two distributions for each of these indices for this homogeneous fire zone that we labeled Fire Zone 9, the Southern Prairie Zone. and under the all forcings in blue and the natural forcings conditions. So basically comparing the present decade with the decade that might have been if we hadn't emitted all that greenhouse gas. And you see that all of these distributions are pushed somewhat to the right in this climate model as a consequence of the forcing on the climate model. If you look at the driving variables that come out of the climate model and ask how those variables have changed, and you see a very big response in temperature, and you would clearly say that the surface air temperature in that region today is substantially different than it was during pre-industrial conditions. These two distributions are discernibly different. There's very little difference in relative humidity. That's something that we would expect. There's a substantial difference in surface wind speeds, which is something we did not expect to see in this climate model. Very little change or slight change in precipitation. So it's drying and temperature that seem to be the driving factors in changing these indices. The other thing that's plotted here are the values of these indices that the Zwiers, if I'm pronouncing it correctly, the Canadian Wildfire Information Service extreme levels. So these are the values of these indices that this system considers to be extreme. And you see that in the case of the fire weather index, it truly is extreme relative to the distributions that are simulated by a climate model. It's somewhat extreme in the case of the fine fuels moisture code. It's not so extreme for the drought moisture code or the drought code, Duff moisture code or drought code. And so it's pointing at some warts in our ability to model these indices using climate model output. If we try to ask a question about whether or not there has been human-induced change, then we could try to calculate these numbers, P1 and P0, probabilities of some event under present conditions and historical conditions. And the way in which we do that is to consider areas under these probability distributions to the right of the levels that are considered extreme in the Canadian Wildland Fire Information System. So we calculated probability P0, probability P1, that's a bigger area, so P1 is bigger than P0, and that's done for all four of these indices, and you can see that all of these cases, this probability P1 representing the chances of, quotes, extreme value of this index under current conditions is elevated compared to previously. So you can calculate a fraction of attributable risk, and you can see that that fraction is very high. In the case of the fine fuel, in the case of the fire weather index, it's about 90%. About 90% of the odds of experiencing an extreme level, according to the model, are due to human influence on the climate system. And so you might draw some inference from that. Nevertheless, the probability of sufficient causation, was this necessary to cause the event, is very small. And in fact, that's what we're seeing throughout the world when we consider heat events. So we are driving the system in such a way that we're raising the odds of a particular event, but we haven't driven it far enough that that event is becoming regular in the sense of the probability of sufficient causation becoming large. Okay, very briefly on the Calgary floods, I think I have 5 minutes left or so, 10 minutes. This is another event that was referred to this morning, 100,000 displaced people, 5 deaths, second costliest or perhaps costliest event in Canadian history. It was certainly noticed by Munich Re in 2013. Munich Re classed it as the 5th largest loss event globally. So it ranked right up there. And in this particular case, the insured losses relative to the total loss was relatively small. You can see how the damage occurred in Calgary. There are no overhead lines here. All of the communications infrastructure, all of the electrical distribution infrastructure, for example, is underground. You can imagine what happened to all of those underground communications and electrical lockers and why that place was shut down. So with a young graduate student at the Université de Québec à Montréal, we studied this using a different model. We used an approach where we did condition on prevailing sea surface temperatures. And the question here is whether or not extreme precipitation, as defined by extreme precipitation average over this entire area, the little basin that produced the flood is about there. It's the Bow River Valley. On this particular scale, you can discern human influence. And you can see that the frequency of the event that occurred on this scale was doubled, roughly, as a consequence of human influence on the climate system. That's typical when we're considering a moisture type of event. The magnitude increased by about 10% on that scale. The model is of fine enough resolution that we were able to ask the question on the scale of the Bow River Valley. And on that scale, the signal-to-noise ratio is such that it becomes very difficult to be able to discern whether or not there was human influence or whether or not the odds had changed. There are many factors here. It wasn't a particularly extreme event from a meteorological perspective. The basin that received the precipitation certainly received a lot of precipitation, but it wasn't a 100-year event or anything like that. It received at a time when the basin was still full of snow. So we have a rain on snow type of event. The ground is frozen. The warm rain helps to melt the snow, so there's a lot of snow melt at the same time as a precipitation input. A lot of water rushes downstream. It can't be absorbed into the land surface because the land surface is frozen. And so where does it go? It ends up in the basements of Kelowna. And so there is perhaps a discernible human influence, but not one that you would say is overwhelming. Another event that we've studied is a very hot summer that was experienced in China in 2013. Official records in China indicate crop losses of the order of $10 billion. Nothing in the records about numbers of human losses, but you can imagine that they might have been fairly substantial. This was the summer of 2013 in China. This is the Chinese record extending from the mid-1950s through to 2013. 2013 was the warmest summer on record. It occurs once in this summer. This anomalously warm occurs once in 270 years in control simulations of climate models. Those climate models simulate Chinese temperature variability quite well, in fact. It occurs once in 29 years if you consider this entire period of record, which is non-stationary. If you consider the climate that's specific to this period at the end of the record, where warming due to humans has been taken into account, it turns into a 1 in 4.3 year event, and that implies a fraction of attributable risk of about 98%. We look at heat events like this on this scale across the globe. That's the kind of number that we find these days. The probability of sufficient causation is still not really huge. So it's still not something that's happening every year. It's happening once every 4 years or so. We have also recently studied record low sea ice distributions in the Arctic. So we've heard lots about that, about the Arctic opening and what its impacts might be. And I won't talk about that. I'll move to some discussion now. The only thing I'll say about the Arctic is that the 2012 event, which is the record low sea ice cover event in the Arctic, is one that we estimate using a range of climate models would have been impossible without human influence on the climate system. It might be the first event of that kind, actually, where we can point to the event and say, this is something that's happened because we've warmed the climate and could not have happened otherwise. And if you've looked at Arctic sea ice, since the record that occurred in 2007, that was the second lowest extent on record, we've been at the very low end of the distribution year after year after year in subsequent years, and continue to be there. So some unresolved issues with this event attribution business, which is now about 10 years old. So event characterization, do I talk about a class of events and an individual event? Do I use a risk-based approach to analysis? Do I use a storyline-based approach? Those are kinds of questions that remain open. There isn't a huge body of practice yet where this has gelled into a single approach. I should point out that discussing an individual event and using a storyline approach are not quite synonymous. There are approaches that are available where we can assign odds to individual events that have occurred, such as demonstrated in a very nice paper by a young guy by the name of Alexei Hanneman. We need to worry about event definition. We need to worry a great deal about dependence on models. So as you've seen, the numbers, the hard numbers that come out, these probabilities that allow us to say something about whether or not humans have influenced the event, come out of climate models. There's very little constraint that comes from observations, and this is so we're very dependent on models in making these kinds of assessments. If we condition on something, then we have to accept that there will be uncertainty in specifying the counterfactual state that we're conditioning on. We've observed a set of sea surface temperature anomalies. We know what the base climate is that we add those anomalies to. For the present climate, we need to estimate what the base climate was in 1850 or 1900, that those same anomalies are added to. So there's uncertainty in estimating that base state. There's also uncertainty from a process-based perspective, because we don't know whether or not the climate system as it functioned in 1850 would be as likely to have produced the same pattern of anomalies as was observed this year. And so the actual frequency of occurrence of a particular pattern of anomalies might have changed with time, and that complicates the evaluation of these probabilities. There's a selection bias issue. We're studying events that bite us. So we know that a big dog has bit us, and now the question is, you come to an expert and you ask, well, how big was the dog really? We already know that the dog was big. This isn't a particularly objective way to proceed. And so what we do need is an objective approach to selecting events so that we can analyze those events on a routine basis, and on the routine basis estimate these probabilities, and over time determine whether or not these probabilities are consistent with actual probabilities of occurrence. That's something we do for weather forecasts. It's not something that we're yet able to do for event attribution. And then there's this communications trap that we fall into, and we need to think about as scientists every stage of the communications process. And there are various opportunities available for us to communicate. While the event is happening, when we know very little, a couple of weeks later, while the event might still be in the eyes of the media, when we've done some preliminary analysis, we can say something, but we need to be careful, and then subsequently, after we've had time to look at the event in much more detail. So thank you very much for your attention.